Hello everyone, welcome to my calculus lecture. In this lecture, we continue to study how to calculate limits. In particular, we study limits involving trigonometric functions. So let us start with the limits of basic trigonometric functions. In this case, basic trigonometric functions are sine of x and cosine of x. Okay, so let's take a look at the following theorem. For any real number a, limit of sine of x when x approaches a is same as sine of a. Likewise, limit of cosine of x when x approaches a is given by cosine of a. So what does it look like? This must look familiar to you because we have seen a similar property uh, with the polynomials, right? Or rational functions too. So, if you remember the reason why, polynomials or rational functions have such a nice limit property is that they are, in fact, continuous functions. We haven't talked about continuous functions yet, but that's what it is, okay? And the same actually reason applies here too. Sine of x and cosine of x, they do satisfy this kind of a nice limit property. It's because they are continuous functions. Okay, so we are going to talk about continuous functions later on, but this is very nice. So in other words, when you find the limit of sine of x and cosine of x, right? All you have to do is just plug in this case, limit of sine of x when x approaches a, all you have to do is just plug in x equals a, resulting in sine of a, okay? The same goes for cosine of x also. Okay, so limits of, what about, other trigonometric functions, like we have tangent of x, secant of x, cosecant of x, cotangent of x, right? Okay, it turns out that limits of other trigonometric functions stem out of these two limits. For example, limit of tangent x, okay, tangent of x, when x approaches a, can be obtained by tangent of a. So how do we know this? To see that, to talk about it, let us move to my notepad. So here we want to evaluate limit uh, x approaches a, tangent of x, right? Okay, so actually we want to show that this is going to be tangent of a, knowing that, knowing those two, that limits of sine of x and cosine of x we just talked about. Okay, so first thing is we are going to write down tangent of x as sine of x over cosine of x. Okay, that's what the tangent of x is, right? And then if you remember, okay, right, so do you remember this property? Limit of f of x over g of x when x approaches a equals limit of f of x when x approaches a over limit of g of x when x approaches a, right? Remember this property? Now, in this case, this property works provided that limit of g of x when x approaches a is not equal to 0. Okay, it's not equal to 0. So that's the additional condition. Let me put a box around this property here. Okay, so in this case also, assuming that limit of cosine of x is not 0, okay, where we know that actually it could be 0, depends on what a value is, right? But in this case, let's say, assuming, right, limit of cosine of x is not equal to 0, using this property, right, this will be limit of sine of x when x approaches a all over limit of cosine of x as x when x approaches a. Okay, so that equals where we have already talked about, right? So we know what the limit of sine of x and limit of cosine of x is. So limit of sine of x is x when x approaches a is going to be sine of a over also likewise cosine of a. Okay, so limit of tangent of x when x approaches a equals sine of a over cosine of a, which is equal to tangent of a. But let us not forget an important condition imposed here, right? In order for this formula, right, to make sense, cosine of a is not equal to 0, right? So let me write down, provided, okay? So this is true, provided cosine of a is not equal to 0, okay? That's important. All right, so let's get back to my lecture slides. Okay, so we're going to talk about actually a very, very important and useful tool for calculating, certain type of limits. Okay, so that's called the squeeze theorem, right? Interesting name. Before we do that, let us take a look at the following theorem. So suppose that f of x is less than or equal to g of x near x equals a. So that inequality, what it says is that that inequality doesn't have to be satisfied, all over the domain, okay? But, just near some point, x equals a, right? So, here near means that like on an open interval containing a, right? So, f of x and g of x are satisfying this inequality. And both limit of f of x and limit of g of x when x approaches a exist. Then what we know is, the limit of f of x when x approaches a is also less than or equal to limit of g of x when x approaches a. Okay, so this is an important theorem. Right, so this leads us to the following corollary. Okay, its name is squeeze theorem, or some people also call it sandwich theorem. All right, and you will see why it's named like that. Okay, in a moment. So here goes the statement. Suppose that we have three functions. Okay, so f of x, g of x, and h of x are satisfying the following inequality. Okay? So f of x is less than or equal to g of x is less than or equal to h of x. So in other words, g of x is in between two functions, f of x and h of x. Doesn't have to be true all over the domain, but just near, like on a small open set, open interval containing a, so near x equals a. In this case, if the limit of f of x and limit of h of x happen to be the same, then basically what it says is that, like, when that happens, so f of x and h of x, they are uh, going to the same value when x approaches a, then the middle guy is being squeezed, so it has nowhere else to go but to the same value, L. So in that case, limit of g of x when x approaches a has to be also L. Okay, so the name makes sense, squeeze theorem or sandwich theorem, right? Okay, so this is a very important theorem. Right. As I mentioned earlier, squeeze theorem is useful for calculating a certain type of limits. Okay. So here is an example. So use squeeze theorem to show that, limit of x squared times 1 over x when x approaches 0 is 0. Okay, so let's talk about why it is. Okay, so I'm moving to my notepad. All right, so we want to calculate this limit x approaches 0, x squared sine of 1 over x. Okay, now maybe you might be thinking about, like, this, right? So property f of x, g of x, right? When x approaches a equals limit of f of x when x approaches a times limit of g of x when x approaches a. Okay, so if we are thinking about this property, okay, we got a problem. I mean, you might be thinking that, oh, in this case, the limit of x squared when x approaches 0 is 0, so yeah, that's easy, right? So what's the big deal? No, because that's not a problem, but the problem here, the second part, the sine of 1 over x, right? We actually we do know that limit of sine of 1 over x does not exist, right? Does not exist. Okay, because the sine of x, as x approaches 0, it keeps oscillating, so it actually goes nowhere, right? So limit does not exist. In order for this property to exist, both limit have to exist. Okay, so you can't just apply that, right? So we gotta try something else. Okay, and so this is irrelevant in this case. All right. So here we go. Where sine of 1 over x. So there is one important aspect of the sine function you have to remember. Sine as well as cosine also, right? Okay, they are bounded by -1 and 1. In other words, so sine function oscillates, but in between -1 and 1. You remember that, right? So the smallest possible value sine can take is -1 and 1. Okay, so that's starting point. Now, what we are interested in is this function, right? So how its limit is gonna be. So x squared sine 1 over x, right? So that's what we want to get. So multiply this inequality by x squared. X squared is a positive, right? Positive, non-negative, If x is not equal to 0, it is positive. And you know the property of inequality, right? If you multiply given inequality, right? So, by the same positive number, inequality does not change. Okay, so if you multiply each side of inequality by the same non-negative number, in this case x squared, so left-hand side becomes negative x squared. The middle part becomes x squared sine 1 over x, and that's less than or equal to x squared. So we have this inequality. Now we are going to take the limit. Okay, we are going to take the limit. Remember the theorem we just talked about. Okay, so in this case, since these three functions satisfy this inequality, right? Oh, actually, not the theorem. We're going to apply here uh, the squeeze theorem. So how does that squeeze theorem is applied to this case? Here note that limit of negative x squared, okay, when x approaches 0, and also limit of x squared. When x approaches 0, they both are equal to 0, right? Okay, so these two, the limits exist and they approach the same number 0. So by squeeze theorem, the middle guy has to go to the same number, right? When x approaches 0. So limit of x squared sine 1 over x when x approaches 0 equals 0. Okay? So we got it. So here we use the what? By the squeeze theorem. Okay? By the squeeze. Oh, apparently I forgot how to spell squeeze. Right. So the one I wrote earlier was correct. Okay? Squeeze theorem. Right. So by squeeze theorem, we get this limit. Okay? So far, so good. Okay, so let's get back to my lecture slides. Right. So the following graph shows you the uh, the function y equals x squared sine of 1 over x. Okay. So as you can see, actually these two blue lines. The top one is a graph of x squared. The bottom one is a graph of negative x squared, and the so in blue, right? So those are the two parabolas, x squared and negative x squared. And the graph in red is actually graph of x squared sine of 1 over x. So they keep oscillating while, like when as x approaches 0, right, the graph both, either side, from the left and right side, they are both approaching, the number 0, right? Okay, so, also this graph of y equals x squared, sine of 1 over x clearly shows you, shows clearly confirms the limit we just calculated. Okay, so another important limit involving a trigonometric function, all right? This is very important limit and useful. So I'm gonna introduce you this as a theorem. So limit of sine of x over x when x approaches 0 equals 1. Okay, right. I'm not gonna prove it, this theorem here, but if you are curious about that, then I actually uh, talked about two different proofs. Okay, one uses something called power series, and the other one uses more like the what is that? The basic just the properties of the trigonometry. Okay, geometry, right? So just using geometry and trigonometry, we could prove also this limit, and right, and also the using squeeze theorem, right? We can prove this. So if you are interested in proofs, okay, I want you to take a look at my lecture note. Okay, at the end of my lecture slide, I wrote down the website address of my lecture note. So anyway, here in this case, I'm going to just introduce you this limit without proof. Okay, so let us take a look at the following examples. Okay, so basically we are going to talk about a couple of examples that require the use of this, the formula. Okay, let's say. So the first one is find the limit of sine of 7 over x over 4x when x approaches 0. Okay, so to calculate that, let's move back to my notepad. Okay, so here we want to calculate limit of sine of 7x over 4x. X approaches 0, right? So here in this case, the only tool we can use is the following formula, right? Which I introduced to you as a theorem, right? So limit of sine of x over x when x approaches 0, it is equal to 1. So as you can see in this case, this x is what? It is an angle, okay? It is an angle for sine of x. So when this angle and, down here also, this number, they both, coincide. So same angle, right? When they are same angle, the limit is 1 when x approaches 0, right? Okay. So same thing goes for this limit of, for instance, what if like, the sine of the angle is not just simply x, but like 7x. Okay? In order to apply this formula, all right, like I said before, this angle have to be the same. So we gotta have like what 7x down here also. Okay? And when this angle 7x goes to 0, but you know in that case 7 is constant, so 7x goes to 0 means the x goes to 0. So we don't have to say 7x goes to 0, but still just simply x goes to 0, right? This is going to be 1. Okay? So that's what we have here. So you know in order to apply this, what do you have to do? Limit sine of 7x, right? So when you have a fraction, right, you can multiply the numerator and the denominator by the same number. The inequality does not equality does not change, right? Equality does not change. So x goes to 0. That's what I'm going to do. I'm going to multiply the numerator and the denominator by the same number, or in this case, actually, same, the angle, all right, 7x. So 7x times 4x, okay, right? And also here, I have to have a 7x, okay? So I am multiplying, here, I'm gonna actually circle around those, right? I'm gonna multiply sine of 7x by 7x. Also, I'm multiplying 4x by the same number, 7x. Okay? Now, this can be written in the following way. So, limit x approaches 0, right? So, sine of 7x over 7x, okay, times 7x over 4x. You can write it this way, right? So this second guy here, like the numerator and the denominator, they both have a 7x in common, so we can cancel it out. Again, canceling is not, actually a correct terminology, but we understood it as what? Dividing the numerator and denominator by x. Okay, all right. Okay, so 7 over 4 is a constant. The constant multiple can be brought outside of limit. Remember that? That's one of the very, the important, limit properties, right? So the constant, we can move it out. 7 over 4, limit sine of 7x over 7x when x approaches 0. Now you know what you see? That's exactly the limit we were talking about earlier, right? So using the limit that, this important limit, right? This whole thing, goes to 1, right? Right, so this equals 1. So overall, the limit is going to be 7 over 4. That's easy, right? That's easy. Okay. So now let us take a look at the next example. Find the limit of cosine theta minus 1 over theta when theta goes to 0. Okay, right. So let us talk about that. So I'm going back to my notepad. I'm out of space, so I'm going to move to next page. Okay, so we want to calculate limit cosine theta minus 1 over theta when theta goes to 0. Now, again, uh, let us first calculate directly, see what happens to the numerator and the denominator when theta goes to 0, right? So when theta goes to 0, right, the numerator, cosine theta goes to 1. So, 1 minus 1 equals 0, right? So the numerator goes to 0. The bottom part also goes to 0. So this is a 0 over 0 type, okay? 0 over 0 type indeterminate form. Right. So somehow also in this case, the only tool we know, in this case is the following formula: limit sine theta over theta when theta goes to 0 equals 1, right? So that's the only tool we know of it. So somehow we have to use this formula, right? But we don't have a sine, we have a cosine. But sine and cosine are closely related by how? If you remember this formula, right? Cosine squared theta plus sine squared theta equals 1. Do you remember that? Okay, right. So using this formula, right, you can write cosine theta in terms of sine and vice versa. In other words, you can also write down sine theta in terms of cosine. So in this case, sine squared theta is going to be 1 minus cosine squared theta, right? Okay. But we don't have that. Okay, we don't have 1 minus cosine squared theta, but what we have is here is cosine squared theta minus 1. Okay, so here's another thing you will have to remember. Do you remember this basic formula, right? A plus B times A minus B equals, A squared minus B squared, right? Okay. In fact, I don't even have to bring this up, but the 1 minus cosine squared theta, actually yes, right? So 1 minus cosine squared theta, using this formula here, right? Down here, it is factored to, so it goes both ways. If you multiply these two, you get a squared minus b squared, or a squared minus b squared is factored into a plus b times a minus b. So, a plus b times its conjugate, right? So this is factored to 1 plus cosine theta 1 minus cosine theta. Okay, so this tells us, this hints us what we can do about this. So limit theta goes to 0. So what you have to do is multiply the numerator cosine theta minus 1 and the denominator theta by the conjugate of cosine theta minus 1, which is cosine theta plus 1 over the same thing, cosine theta plus 1. Okay, so that equals limit theta equals 0. So these two, if we multiply, we get cosine squared theta minus 1, okay, over theta times cosine theta plus 1. Okay, we have that. Now, cosine squared theta minus 1, we know what it is, right? Cosine squared minus 1 is going to be from here. We know that that's negative sine squared theta. So negative sine squared theta over theta times cosine theta plus 1. Okay? Let's continue. Yeah, here. Okay? So that equals negative sign, that's, constant negative 1. So, I can put it outside of limit theta goes to 0. We can write this as, remember sine squared theta is, sine theta times sine theta. So you can write that as sine theta over theta times sine theta over cosine theta plus 1. Okay? So in this case, let us take a look at the limit of the first part and second part when theta goes to 0 separately. So limit theta goes to 0, sine theta over theta, as we know, this is by the theorem 1. Okay? And limit sine theta over cosine theta plus 1, theta goes to 0. What happens? So in that case, when theta goes to 0, sine theta goes to 0. The bottom part, cosine theta plus 1 goes to 2. So that's going to be 0. Okay? So their limit, both, both limits exist. In this case, we know this is going to be negative 1 times 0, which is 0. Okay, so we just showed that the limit equals 0. Okay, I try to make my lecture the less than 30 minutes, but it became like a little longer than that. Anyway, so that would be it, and the more details of my discussion here again in this lecture can be found in my lecture note at the following address. Okay, so as usual, I made a hyperlink here, so you don't even have to copy, but you just click on this address. It'll take you to the note. Okay, and also if you want to access my actually the blogger site where you can find the other the lecture notes, right? Simply this is also hyperlinked, so simply you click on blogger. Okay, all right, so thank you for watching, and I'll see you next time. Bye bye.